5.8. So, like, it would be definitely like church 6.5. Yeah. And when I see that, I just kind of like round up. I'm like, I have to use that somewhere.
Oh, God. Oh,
Good morning, Ewan.
Are you going to take it back to IGS?
Yeah, I hope I can.
Hi. Hi.
I tell them like they're supposed to like change the permissions on it. That's true. Because I went to the first time. I just your hard drive probably corrupted, and then I just use that. It's not corrupted.
Updated.
Or like you just weren't like you were denied permission to access your hard drive.
Okay, we've got 8:30, so why don't we get started? Good morning, S&P.
Good morning.
Wow, that's a great start to week number 11. Can't believe we're on the 11th week, but here we are. And today's exciting because we're going to be changing our sensory modalities. We're going to be moving from vision over to hearing. And that should be interesting because it's a different physical stimulus. It's also a different cranial nerve for us. Does anybody remember which cranial nerve the optic nerve was by number? Yeah, second cranial nerve. Okay, now we're moving off to the 8th cranial nerve. And just a couple of announcements before we get into any of that detail. We do have our paper due on Friday. I'm looking forward to the student-generated discussion. And we'll be talking about issues in deafness, and we'll see some power and justice issues related to deafness. So a really nice way to start out this section is we'll talk a little bit about the physical properties of sound, and then we'll talk about some of the physiology of sound, and then we'll talk about some social justice issues when we have hearing deficits. So I think it'll be a very interesting week. One other note about this week, just for the students who are in the research component of this course, we are up to the point where most of us are collecting data. So we typically meet on Tuesdays and Thursdays. I will still be available that time. You may or may not need to come in, depending on what your group needs to do and when you're running your participants. So I will be there, and you can be there as you need to be there, but I recognize that sometimes people don't need to be there at that particular time because they're not collecting data. They might be collecting data in the evening instead. Okay? All right, really good. So why don't we begin to get into today's discussion, and we'll remind ourselves of some of the orienting questions that we have for our semester. And you might remember this question. By show of hands, who remembers this question? Why do things look as they do? Remember people ask, okay? So now we're going to be asking the question, why do things sound as they do? But we could be talking about really any sensory modality. So now it's, why do things sound as they do? And I wonder if anybody can begin to give us the two broad answers to that question. Why do things look as they do, or why do things sound as they do? Two broad approaches to that. Anybody recall? Okay, thanks, Becca.
Because the stimuli and the environment are as they are.
Okay, really good. Because the world is as it is, okay? Things look as they do because the world is as it is. It's a very environmentally focused kind of response to that question. Or things sound as they do because the world is as it is. Okay? What's another answer to that question, rather than focusing on out here in the world? Yeah, go ahead. Okay, because we perceive things as they do, or actually because the brain is as it is, right? Okay, so why do things look as they do? Well, because the world is as it is, and because the brain is as it is. And we could say the same thing for sound. That really sets up our first two sections today, for this week, I should say. Today we're going to be addressing what's there out in the world, and then we're going to be talking on Wednesday about how is the brain responding to that stimulus out in the world. And then on Friday, again, we'll be having some power and justice issues. So hopefully you can see a connection. Even though we're moving to a different sensory system, we're still interested psychologically in why do things look as they do, sound as they do, and so forth. Okay? Who's all right with that? All right, that's one of the ways of getting into this. All right, so we had a lot in our PowerPoint presentation that you saw for today. We talked about these three components, amplitude, frequency, and phase, and I thought what we might do is divide our time today into these three components. We'll spend some time discussing amplitude first, frequency next, and phase, and these should look pretty familiar to you. What's missing, by the way, from FAPO? What idea is missing? Yell it out. Go ahead, Jen. Orientation is missing. So we see some similarities between the FAPO in vision and FAPE here, where we don't have an O in the auditory domain. So it's actually a little bit easier in that way. Right? We're missing our O. Okay, why don't we do it just like this? I'm going to go to a different view than I normally use. I'll go to the slide sorter view, And let's have you focus on amplitude for a moment or two, and we'll have you be teacher. I wonder if we can have you find a partner, and maybe you can explain some concept in here to your partner for a moment or two, and then we'll have you switch. You'll become the student then, and your partner will explain to you some concept related to amplitude. We'll go just that far. So I'll leave these up here. You might have the printouts in front of you, but if you don't, you can take a look here. You'll find a partner and explain to them something that that might be relevant to amplitude, and we'll pretend that your partner doesn't know about that aspect of amplitude. Okay? So maybe we can have you two be a pair, if that's all right, and we'll have you two be a pair, and then we'll have you two and you three, okay, and then you two. Did I get everybody, or did I leave somebody out? Okay, so move your chairs around. We'll have somebody play teacher for a moment or two, and then somebody play student. I'll yell switch after a couple of minutes. Teach your partner something about amplitude, if you're the teacher.
Oh, I'm sorry.
Okay, fine.
There has to be so the different sound or position sound has to have a medium to sound through, so the medium needs to make the sound through there, but technology is acting like light now. And measurement Pascal. Oh, and sound travels average in 143 meters per second. And but that will change versus what medium sound needs to go through, whether they're more solid. Start on 10 meters. And tuning forward is not. So let's discuss the idea that the number of molecules sound can be in pretty compressed, which that there's some amount of molecules in a small space versus refracted molecules in a large space, and that changes sound.
Oh, okay. Okay, so yeah.
Pretty much trying to like a log unit,
Okay, when you come to a convenient stopping point, can you switch? Can your partner now teach you something? We'll switch roles, and ideally we talk about a different aspect of amplitude, but go ahead and finish your thought if you're midstream, and then you can transition when it's easy for you to do that.
Alright, so decibels,
Okay, so
not arithmetically, but mathematically, the decibel is equal to 20 times the log of the whatever pressure you're trying to measure divided by standard pressure. So,
Hi, Michael.
all these ideas together, if you think about it as you're trying to, with the amplitude, you're trying to figure out how much the vibrations of whatever is making a sound, you're figuring out how much it compresses the air, how much more compressed the air is versus like ambient pressure around you, versus how much more it gets stretched out. ambient air that help me
Maybe it's just too high, maybe or
like
something.
really understand the amplitude.
Yeah, sort of level off.
And use that.
And
So June, they're teaching each other about amplitude. We're playing teacher, student, and they're teaching each other about amplitude. Okay, that's all right.
And I don't know where the 20 comes
range
from.
over which you're
But 20 is there. It
by
might
using weight.
be because
And so
the
if I'm
standard
talking
pressure is
1
20
gram,
micropascals. But
whereas Dragon Beetle is 1,000,000.
Why don't we do one more moment?
the back sound has to have a medium to travel through. And for air, so yeah, travel through a vacuum.
It's a relative concept. Because I did 1 times 10 to the 15th. So that was I don't remember how I.
Okay, why don't we draw the line there? Sorry to cut you off midstream, but we'll hopefully we got you warmed up and we got you thinking a little bit about amplitude and we got you practicing this. So I wonder if anybody wants to share with us what they taught about. Anybody want to help us with any aspect of amplitude here? Okay, thank you, Jenny.
Well, to start off, we talked about the amplitude of a wave is kind of like the distance from the peak to the trough.
Okay.
So, a very higher amplitude wave that has a larger distance between the peak and the trough will be like a louder noise than
Okay.
a smaller amplitude wave.
Okay, that works. If we can pause just right there. I wonder, it's been a little while since we've done the wave. Can we do the 2 different kinds of waves today? So we'll ask you to put your hands up and down, and we'll see if we can get our transverse wave going. Remember that we have a transverse wave and a longitudinal wave. We'll do the transverse wave first, if you recall what that is. You'll go up and down with your hands. I won't ask you to stand, right? And I'll go back and forth, and you can just follow me, all right? So let's see if we can get our wave going in the classroom. All right, that's pretty cool. All right, all right. All right, so that's our transverse wave, and Jenny's talking about amplitude. I wonder if we can do a lower amplitude transverse wave. We'll stay on the transverse wave. Can we give me a really, really low amplitude transverse wave? Let's see what that might look like. I'm going to go back and forth. Okay, now can we amp that up? Can you give me a much greater amplitude? When we're amping it up, there it goes. All right, all right. And perceptually, what's going on when we amp that up? It's louder, okay, right? So that's all very intuitive, I hope. Thank you, Jenny. That was a good start. Did you want to say more about that? So you talked about the peak to trough difference, and people were signifying that by going up a little and down a little, or up a lot and down a lot. Anything else that you want to add there, or was that how you wanted to get us started?
I got started.
Okay, thank you. That's a good help. Thank you, Owen. Yeah.
And then, well, we're talking about peaks and troughs, but physically what that actually is, we're talking about the compression of the air.
Uh-huh.
We're measuring how much more the air is getting compressed and stretched out or rarefracted versus the standard pressure in whatever medium this vibration's traveling through.
Great, right. So we're really talking about how compressed the air is when we're talking about its amplitude. And so we have to now move to that geek wave, the longitudinal wave. Who remembers doing the longitudinal wave once earlier? Okay, so that's really the one that's going to be relevant for today. We can always think about waves in general as traveling disturbances, but light was the one that was traveling as a transverse wave, and as you can see here, and I hope you'll pardon my abbreviation, it's really, we can get a better approximation than that. It might be more like 2.99 and some change, but if you'll allow me to keep the 3's the same, just for simplicity, 3 times 10 to the 8th is the speed of light versus 3.43 times 10 to the 2nd is the speed of sound. And so the speed of sound, of course, is a millionfold slower, and it travels as a longitudinal wave. Can we do the longitudinal wave? We'll get into position for that. There, okay, Owen's in position, all right? And we'll try this, and we might want to move our cups out of the way. Some people have brought in their morning coffee, and this is always bad news when we have the longitudinal wave going on. So I think Molly's got an accident almost waiting to have. All right, there we go. Thank you, Molly. All right, here we go with our longitudinal wave. All right. And remember that don't move until you're almost hit by your neighbor. You don't have to physically hit your neighbor, but wait until you're almost there and stay with me. If you can, you kind of have to look in two places. Okay? And then back over. All right, and we'll do one more, and I'll freeze us as we go right here. Maybe I can catch Yuen and Jenny. Can we have your hands come together? So you can even stay there. If you can just put your hands together. Sorry. Okay, so this is really compressed air, and if they pull out just a little bit, it's less compressed, and as they're all the way away from each other, it's fully rarefied. Okay, so when they're really close together, that would be a peak. That would have been way up here in our transverse wave. When they're very far apart, that would be a trough. They're way down here. So compressed and decompressed air, or rarefied air. We're talking about just how intense that can be, right? How much amplitude we have there. Please go ahead.
I just have a question because so when the air is compressed and they're close like that, she's also far from this side.
Yeah.
So which one do we measure? Like, how do we know?
Right. Okay. So that's a very good point. We can ask when those air molecules, if I can call them that. It's really not all that scientific to talk about an air molecule. We can be more precise than that. But for our purposes, we'll talk about molecules of air, and we can ask how, at their maximum compression, how compressed are they? And the unit of measure, thank you for that question, the unit of measure would be the Pascal. Okay, we're going to be, as you probably shared with your student, or your teacher may have shared with you when you were playing teacher-student, the baseline or standard pressure is going to be 20 micropascals. Okay, so we can, to get back to your question, we can say when they're maximally compressed, we can measure that. Okay, and then
Also measure that they're maximally rarefied.
we wouldn't have to. We would just assume that one of those measures is enough. Okay, right? So here's the Pascal. Who remembers hearing about maybe Pascal's triangle or Blaise Pascal as the French mathematician? He's the one who gives us this unit of pressure. And this is just a little bit of the physics, in case you wanted to know. This is defined as newtons per square meter. Okay? And you might know that Newton was famous for coming up with for many things, but among them coming up with his unit of force, which would be mass times acceleration. Okay? And there are ways of defining all this. We can take a 1 kilogram mass and ask how much force does it take to get that thing moving over 1 meter at over a time of 1 second, or actually 1 second squared. When we talk about acceleration, we are in squared time units, a little bit counterintuitively. So those are some of the basic physical principles that we have going there. I also wanted to develop just a little bit of our intuition about this. We've done now the longitudinal wave. That's always a little bit more awkward. When we do the longitudinal wave, it moves more slowly. In this case, light versus sound, as I've mentioned, is a millionfold difference. I wanted to give you an intuition about what a millionfold difference might be. So let me see if I can give you this as an example. Who's been at the Granville Inn before? Okay. So we know where the Granville Inn is, right on this corner of North Pearl Street and Broadway. So if you can imagine walking from the Granville Inn, turning right onto North Pearl Street and coming up to our entrance right over here on the campus. We have that East Gate entrance, which is very near Mitchell. You can get onto the campus that way. So if you walk from the Granville Inn to that entrance and back, you've walked 1 mile. Okay? That's 1 mile. If instead, or if let's say that Kirsten is doing that, she's walking from the Granville Inn to that gate and back for the 1 mile traverse. Let's now try to understand what 1,000,000 miles would look like. If somebody else will say that it's Naomi is going to start her walk, but instead of walking to that gate and back, she walks to the moon and back, and to the moon and back. That would be 1,000,000 mile traverse. To go off to the moon and back, off to the moon and back is about 1,000,000 miles. So if you can imagine that she's making that journey at the same rate at which she's making that journey. I shouldn't say same rate, but she's traversing that distance over the same interval of time that Molly or Kirsten are traversing that distance. Then we have a 6 order of magnitude change in the speed. All right, 1,000,000 miles versus 1 mile. Who's following that? Okay? That's the difference in speeds. It gives you some idea about, if you control for time, how much more distance would you have to travel. So a round trip to the moon 2 times. I find that pretty extraordinary. Okay? But the other thing that's extraordinary about that is when, Emily just raised her hand. In a moment she's going to speak. I see Emily and I hear Emily. And to me, those are all simultaneous. I can see her mouth going and I can hear her voice. And yet somehow the light from her mouth came to me 1,000,000 times faster than did the sound from her mouth. And yet it all feels psychologically simultaneous. Interesting, right? But they can't really be arriving at my head at the same time, but I experience them as simultaneous. Okay, now for your question.
I'm sorry, could you repeat what you said again about the journey? There's a 6 magnitude
Yes, 6 order of magnitude. So that was a phrase that I introduced. Who's heard of that phrase before? Order of magnitude? Can anybody remind us what that means, if you know what that is, an order of magnitude? Yeah, 10 times, right? A factor of 10, it's essentially a 0, okay? So if we have a 6 order of magnitude difference, we would have 6 zeros or a millionfold, okay? So as I think it was Kirsten I had making that trip, she's making her 1 mile trip, Naomi's making a 1 million mile trip over the same interval of time. Okay? 6 order of magnitude change. Some of the amazing events, you might also be interested in this. There's lots of great, amazing acoustic phenomena that have occurred here. There was a very famous volcano called Krakatoa. Has anybody heard of that volcano, Krakatoa? The claim is that if Krakatoa had gone off in the city of San Francisco, you'd be able to hear it in New York. That's how much acoustic intensity there was. Right? You could hear it all the way in New York. That's a pretty good distance. Right? Another really big acoustic event would have been when that meteor came in and landed in the Yucatan Peninsula, maybe 65 million years ago. The Yucatan Peninsula is near Mexico, and we believe that that's probably what wiped out the dinosaurs. Okay, the claim is that would have been heard everywhere on Earth. That would have been enough acoustic intensity that it would have been heard everywhere on Earth, and you would have gotten this longitudinal wave moving around the Earth, and some people have speculated that it might have moved around the Earth multiple times. So in comes the meteor, lands near Mexico, it makes this big splash, everybody hears it, every animal that's got any acoustic sensitivity would hear it, and you might hear it a couple of times, depending on how long it takes for that sound wave to go around the Earth. Okay? Pretty interesting. Pretty interesting. You can imagine how many animals would have been deafened. They would have blown their ears out if you were somewhere near there. Right? Pretty amazing acoustic events. Okay, let's go to other comments that we have so far on amplitude. Well, in a few minutes we'll move over to frequency, but we do want to spend some time on amplitude, and we have a couple of nice demos to do with that. Please go ahead, Becca.
We talked about how we can begin to appreciate our capacity to fire neurons in response to sound.
Okay, great.
And you can think about it as in terms of, in the context of weight, a thumbtack weighs 1 gram.
Okay.
Whereas a Volkswagen Beetle weighs 1,350,000.
Okay. All right.
And let's see. Yeah, this gives us an idea of the tangible idea of like how intense we can hear. If you multiply, I believe this is how you do it, if you multiply 1 thumbtack times 10 to the 15th,
okay.
That's how many Volkswagen Beetles you need to represent the high end.
Okay, all right, so yeah, lots of ideas there. So thank you for getting us onto a few notions there, and that is we have to have a nervous system response to that incredibly intense stimulus, and we can ask over what range will our nervous system respond? So this was something that I mentioned in the video, and it's almost like drawing a psychometric function, okay, where I'm going to have over here in this case response rate. And this will be the response rate, the number of action potentials that we get. And this will be something like intensity. I'll leave it as an I. And at really, really low intensities, it might be that the nerves that you've got, or the neurons that you have in your auditory system, don't respond at all. Something is so soft that it doesn't respond. We've already seen an example of that. Earlier in the semester, we started out with a demo. We were learning about psychometric functions. And I played for us some tones that all of us can hear. And then I played a higher frequency, and we could all hear that. Then I played a higher frequency, and I couldn't hear it, but you could. Okay? So there was a point at which my neurons were firing, and then they stopped firing because it was but you all could hear that. So your neurons were more sensitive than mine. So what happens is at relatively low intensities, we might have absolutely 0 firing and still 0. And then at some point, your nervous system begins to pick that up, and it levels off at some higher intensity. And we get more and more firing over this range. Who's okay with that? And then eventually, it reaches its maximum. Then there might be another neuron that's less sensitive, in this case. And it needs a higher intensity before it gets going, and it needs a higher intensity before it maxes out, and so forth. And we could just keep on drawing these. And so at some point, maybe when we get that big meteor that comes in, all of your neurons are going to be firing full steam ahead, I think is the phrase I use on the video, and they're all going to be maxing out, and that's as far as you can go. And what we can ask is, what range of intensities do we have that can create some kind of differential response inside of your nervous system that can show some kind of increase from intensity 1 to intensity 2. Please go ahead. Yeah.
So when you have all of your intensity sensing neurons maxed out, and then you hear something louder, that sensation that you get, that's actually like pain receptors kicking in, and it like you feel the pain and you hear the sound, but your ability to sense the intensity is like maxed out.
Yeah.
As you're like feeling more and more pain, you're just getting pain added on.
Sure, right. Yeah, it's an important point because, as we've mentioned before, there actually is a type of pressure here. Right? We really are compressing the air, and that compressed air really is coming and hitting you. So now there can be, separate and apart from the sound sensation, there can be a physical pain sensation. Right now, maybe that has a different range over which that's operating. So we're just at the pure sensation and perception level, talking just about the auditory stimulus. We can ask what range of stimuli would that be. And it turns out to be a 15 log unit range. So we've already made this amazing comparison of a 1 million-fold difference, and that would be a 6 log unit difference. Imagine a 15 log unit difference. That's really quite a range. Okay? All right, so then what we can say is, we'll get back to Becca's excellent example. We have this scale. Who remembers the scales of justice that go like this? Does that sound familiar? On this side, we have the lowest intensity that we can hear. That's 1 thumbtack, so to speak. And then over here we have 1 times 10 to the 15th thumbtacks. And we're going to try to express that as Volkswagen Beetles. Like, how many Volkswagen, would we need? Half of that Volkswagen Beetle, 3 Volkswagen, how many Volkswagen Beetles might we need? Okay, that was one of our pop quiz questions. And we won't have a pop quiz today, but here was a setup for that. Pardon me. Let me go to here. Okay, so we have 1 thumbtack, and a Volkswagen Beetle weighs this number of grams or this number of thumbtacks, and you can see that we're in the millions, right? So we have about a 6 order of magnitude difference between that one and this. Who's okay with that? That we said a million was 6 orders of magnitude because a million has 6 zeros after it. So we're expressing the weight of the thumbtack as 1 gram. And if we now weigh the Volkswagen in grams or in thumbtacks, we have about a million of them. Really, it's 1,350,000, but we'll call it a million. So there are 6 orders of magnitude more of these than that. Okay? But we need to get to a 15 log unit range, not a 6 log unit range. Right? So we need many, many more Volkswagen Beetles. Did anybody try the computation and see how, okay, what did you come up with?
I came up with 40.77.
40, okay, so we'd,
Volkswagen Beetles.
so we'd have 1 thumbtack on this side and 40.77 Volkswagen Beetles on that side. Okay? Anybody come up with a different number? Okay, why don't we see if we can walk through this. This I think you might find interesting. It'll give us a little bit of a review on scientific notation. Who remembers scientific notation? Okay? All right, so let's see if we can do this. We've got this mathematical relationship where we've talked about intensities, the 15 log unit range, and we want to see how many Volkswagen Beetles we actually need. Okay, so let's see if we can get to some of the computations here. And here we go. Here's our first one. Okay, so just to set the stage, we have that as being the weight of 1 Volkswagen Beetle. Okay, it's expressed here in scientific notation. And before I go any further, we'll ask who's okay with that. Does that work for us? We can say it's, a million-ish grams, a million-ish thumbtacks, and then we can express that in scientific notation. Notice that it's to the 6th power. That's going to be at the million level. So that's going to be, it's more or less our measuring stick, right? We want to use that as our unit of measure. And what we're going to do is take our 15 log unit range, and we're going to divide that range by the weight that we have of our Volkswagen Beetle. So how many times does that Volkswagen Beetle go into that? In other words, how many times can this 6th order expression go into that 15th order expression? And we're dividing one into the next. Okay? Who's okay with that? Okay? So far so good? All right, let's see if we can do that. And just a little bit of the tricks that you might remember. I know it's been a while, but what we can do when we have a shared base, this is base 10, that's base 10 also, we can divide the coefficients. So we'll take 1 divided by 1.35. That's where those numbers came from. And then we'll do the same thing for those bases that are being exponentiated. We'll do 10 to the 15th being divided by 10 to the 6th. We'll just lay that out that way. I remember seeing that maybe many years ago. I know that you're probably rusty on that. I get rusty on this myself, okay? But that's the computation that we have so far. Let's go to the next step and see if we can just unpack some of that. We'll just bring this one down, nothing new here. Does anybody remember this trick that when you're dividing exponents, you're actually subtracting them? Who remembers seeing that? Okay? So what we're doing then is we're simplifying this a little bit, and we'll leave this the same, and now we're saying that this gets multiplied by 10 to the 15th minus 6. Anybody want to do that in their head? 15 minus 6 is 9. Okay, so let's see if we can go to the next one. So we have the same expression, 10 to the 9th. Okay, that work for us? Now we'll do this division. I don't expect you to do that in your head. That turns out to be 0.74 times 10 to the 9. Okay? Remember this trick? I can borrow one of these and I can move this over once to the right. So I can now have 7.4 times 10 to the 8th. That work for people? Okay. All right, and then if I now start adding zeros there, I wind up with 740 million Volkswagen Beetles. Okay? 740 million Volkswagen Beetles. Go ahead, Becca.
Oh, never mind.
Okay.
I see how you got the 10 to the 8th.
Okay, 10 to the 8th. All I did was I stole 1 from here, and that allows me to move the decimal point over one time. Okay? So now I wind up with 740 million Volkswagen Beetles. Okay? That's a lot of Volkswagen Beetles, 740 million of those. Okay? So our auditory system can respond to a range of acoustic intensities that would be the equivalent of having scales of justice that have a thumbtack on this side and 740 million Volkswagen Beetles on this side. Okay? That's a pretty good way of thinking about this. That's a 15 log unit range of weights. Who's blown away by that? Okay? Your auditory system has been doing that for you all the time. And only today do we get to appreciate the full range over which that's operating. So that's one of these, 740 million of these. That's the range over which we get from here to here would be that range. Pretty amazing. I've shared this with some teaching faculty, and they said, that's a really spectacular way of thinking about this. But then the problem is, to what extent do students really appreciate, or does anybody really appreciate what 740 million is? Okay, we need to develop some intuitions about that. Okay, let's see if we can do it this way. Does anybody know the population of the U.S. approximately? 310 million, if you'll allow me to call it maybe 300 million, something, it depends on how we count, but maybe 310, 300 million, something of that order, okay? Anybody know the population of Canada? Yeah, maybe another 20 or 30 million people, something like that. So we might need to add the population of Canada. So we're not up to 740 million yet. We're in the low 300s, maybe mid 300s. We might add another country like maybe England or something like that, and we might get up to 370 million. Something. We'll add England. So if we got to 370 million, we'd be half the way there. Who's okay with that? Okay, let's see if we can get a visual going here. We're going to put Owen into the first of our 740 million Volkswagen Beetles, and we're going to have him drive his Beetle up onto our scale. Okay, so Owen's Beetle is there. Then we'll have Briella do it. Then we have Elise do it. And then we have Molly do it. And everybody in the classroom does it. And everybody in Dr. Hudson Como's class does that. Then we go throughout the campus, throughout the town, throughout the county, throughout the state, across the nation. And we have 300 million people. We do this in Canada. We do this in England. And we get to 370 million people. And we're half the way there. Then we have Owen drive his second Volkswagen Beetle up, and everybody puts their second Volkswagen Beetle, and we'd eventually get to 740 million. Okay? So for every man, woman, and child in the US, Canada, and maybe England, driving 2 Volkswagen Beetles onto our my left-hand graph there, that would do the trick. Who's okay with that? Okay? That's a 15 log unit range. Go ahead, Becca.
In this analogy, would grams correspond to decibels?
Would grams correspond to decibels? It wouldn't be a 15 log unit range of decibels, but we can think of that as being the intensity range. And we'll in a moment get back. Well, why don't we use that as our transitional question? Maybe somebody can help us out with this next item. I think we even give you the answer in this next item. We're trying to work with some decibels here. See if we can get to that. Okay, so here's our decibel formula. And this will be the decibel formula for pressures. So if rustling leaves have a dB SPL of 20, so we get 20 over on this side, can somebody help us with what the value must be inside of the parentheses? Anybody want to help us out with that? Okay, we'll have you in, Gil.
So the log of parentheses is 1.
Yeah, right. That's right.
10 to the 1 is like 10.
Yeah.
Because we have, yeah.
Okay.
So the parentheses 10.
Okay, inside of the parentheses we have 10. Okay? Maybe people are familiar with this, maybe they're not. If we take the log of 10, we have, anybody know? How many zeros in 10? Right, okay, all right, there we go. It's one of the ways of thinking about it, right? So if we have 10 inside of here and we take the log of 10, we're at 1. 1 times 20 equals 20, and that's what we have. We're saying that if we had rustling leaves out there on this autumn day, right? That might be a pressure that we might experience. We might go out and be able to measure that. Please go ahead, Owen.
So the rustling leaves are causing a 200 micro.
Wow, that was wonderful. 200 micropascals. Can you tell us how you came to that number? That was correct.
Well, if what's in the parentheses is 10 and the standard pressure is 20 micropascals,
Right, okay.
then they're 200 micropascals divided by 20 is going to give us 10.
Okay, right. So 200 over 20 gives us 10. Who's okay with that? Okay? If we take the log of 10, which is basically very crudely how many zeros are there in 10, okay? If we do it that crude way, we wind up with 1, as you correctly mentioned. 1 times 20 is 20. We started out with 20 on this side. So we won't make a big deal out of that, but that would be some notion of how you could begin to compute these intensities if you wanted to quantify them. And because we're psychophysicists this semester, we're interested in knowing a little bit about the physics of the stimulus out there in the world. And this is how we talk about this, but we're still in the domain of amplitude. Okay? Okay, anything else on amplitude, or can we move on over to frequency? Yeah, please, go ahead.
I don't want to answer this right now, but I don't really quite understand the context of intensity is proportional to pressure squared.
Yeah.
So it's kind of trouble conceptualizing that.
Okay, right. So these are different physical measures. I is equal to p squared. Sometimes we can express the amplitude of the sound using pressure, and sometimes we can express it using intensity. And I wonder if I might offer you this as at least a starting analogy to begin to. We can express length a couple of different ways. We can express length in centimeters or in inches, and we can get a conversion factor. If you wanted to go from centimeters to inches, you'd have a 2.54 scaling factor. Does that work for us? Okay. Two different ways of talking about just how compressed that air is. And two commonly used measures are intensity and pressure. What we were just talking about was a 15 log unit range in pressures, in intensities, excuse me. Okay, so that was the I measure. But if you wanted to use pressures, it would be p squared is equal to I. Does that help? All right, really good. Okay, why don't we move on and see if we can make some progress here in frequencies. And why don't we try it this way? Instead of putting you into groups, we'll see if we can optimize our time. Can anybody share with us anything that's clear to them about frequencies? That's our second of the 3 features. And we started out on this slide. Okay, why don't we have Briella start us out on frequencies?
So basic definition, frequency is the number of cycles per unit time.
Okay.
Measured in hertz, and it's like the pitch of the sound.
Okay, really good. Okay, so we can begin to define it as the number of cycles per unit time, and we usually use cycles per second. Anybody remember the 2 pronunciations of that word? That was it was Hertz or Hertz, okay, which is how I believe the Germans pronounced that. Okay, so they probably wince when the Americans say Hertz, but we typically do. Hadn't thought of that before. Very good. Okay, and she was also giving us a psychological correlate, and that would be pitch, essentially. So we have higher frequency. Okay. Okay. Anybody else want to tell us? Yeah.
And also that frequency and wavelength are like inversely related.
Yeah.
So if the frequency, if you have a higher frequency wave, it's going to have like a shorter wavelength. And then if you have a lower frequency wave, it has a higher one.
Yeah. Okay. So we have this inverse relationship between wavelength, and we're thinking of a cycle as a complete iteration of a pattern. So here we're at some kind of compression. Here we're at the comparable level of compression. We can ask how much time has elapsed over this, right? And here we have peak to peak. We can ask how much time has elapsed. We could have done this also in space, and we did it in space a while back when we had our different spatial frequencies, right? Okay. So now we have these, we might call these temporal frequencies measured in hertz. Okay. Okay. Really good. I thought I saw a couple other hands. Anybody else want to tell us anything more about frequencies? Does anybody know the range of, I don't want to get too far ahead of ourselves, but we can talk a little bit about the range of frequencies that humans can hear. At least we'll talk about young people like you, the range of frequencies that you typically can hear. Anybody have a notion about that? We talked about the range of intensities over which we respond. We can talk about the range of frequencies. This actually wasn't in today's PowerPoint. I thought some of you might know this for other reasons. Yeah, do you have some?
16 hertz to...
Wow. That's perfect. Low end for us is 16 hertz.
low end,
Yep.
And
Okay, yeah, so it goes up to about 22 kilohertz or 22,000 hertz. Now, I might be able to hear that, but I'd need a lot of intensity to hear that, right? That would have to be really, really loud. It might be deafening to you, right? Okay, but I probably could still get there. I don't know if my parents could still get there, but I might if there was sufficient intensity. Okay, so we can hear over that range. So what's going on? As we move from 16 hertz to something like 22 kilohertz, you can imagine that this wavelength is getting smaller and smaller and smaller. Okay, we can think about this as a smaller wavelength in time. We can also think about it as a smaller wavelength in space. That's a little bit difficult for some people to think through. Does anybody remember the point we made about middle C on the piano? There's a point that comes up in the video of middle C on the piano. Yeah, thanks, Owen.
It's got a wavelength of 1.3 meters.
1.3 meters, right? Okay, so remember that through a given medium, light is going to be traveling, and it's going to be traveling at a particular speed. In this case, it would be something like 3.43 times 10 to the 2, or 343 meters per second. Okay? And if we think about those cycles happening relatively quickly or relatively slowly, but the speed, that the wave itself doesn't change speed with its frequency. All the frequencies move at the same speed through that medium, but we can do our little conversion, and we do have a formula over here if we wanted to look at it. See if we can, this kind of a thing. We can get some idea about how long these different wavelengths are. And if you go to middle C on the piano and you push middle C, you'll get a wavelength that's something like 1.3 meters. Okay? And then if I go up an octave from there, I'll cut that wavelength in half. Okay? So that's kind of interesting, that when I'm playing middle C, I'm stimulating your ears by a wavelength that has a measurable extent in space. Right? Pretty cool.
And
yeah,
that's the distance it takes for the air molecules to go through a compression and a rarefaction.
That's right. That's right. If we could see those somehow, we'd see a whole. If we could color them in some way, and if we could make the compressed ones reddish and the decompressed ones bluish, we'd see this red to blue kind of pattern happening over a range that would be 1.3 meters. Then I go on the piano and I hit the next octave up. I hit the next C up, and all of a sudden that whole thing would shrink down to 1/2 of 1.3. So it would be 0.65 meters. Okay. And then I could shrink that down again by a factor of 2 by going up to the next octave and so forth. Okay, that's pretty cool. Now what's interesting about that is, first, just by show of hands, who's understanding that there's a spatial relationship between having higher and higher frequencies and shorter wavelengths? Okay, so if you're a mosquito, right, or you're a bat, and you're trying to catch the mosquito, if you're the bat, you have to be operating over really, really small ranges of space, right? Because that mosquito is a fairly tiny object by our standards. I guess a physicist would tell you that a mosquito is a fairly large object if they work with quarks or something. But from our perspective, a mosquito is a fairly small target, right? So if I need to localize that thing, and I'm going to be using sound to localize it, I have to have a really, really high frequency so that I can squish the sound waves into a region of space that's down at the mosquito's size. Who's following that line of reasoning? Does that work for us? If I have to localize something that's really, really tiny, I need a really, really high auditory frequency in order to get my sonar going, my radar. I send out a sound, I get an echo that comes back to us. And later on in this section on hearing, we're going to be talking a lot about bats and how bats localize their sounds and the different ranges that they use of frequencies in order to get to these really tiny targets. Okay? And you can imagine if that bat is coming in to eat the mosquito and misses by even a fraction of a centimeter, even by a millimeter or so, right? That bat goes hungry and might not live. So that bat actually has to localize over very small regions of space, incredibly high frequencies. Okay. All right, something else on frequency, or should we? Is that a question? Yeah, please.
Question of interest.
Sure.
Low frequency sound waves travel further than high frequency.
Well, they frequently will. Yeah, it's easier to block high frequency sounds. It certainly is easier to block them. And the reason it's easier to block them is you can imagine that there's only so much spatial extent. Here comes one. It's going to hit my head here. It may or may not be able to wrap around depending on how big it is. But if it's really big, it's way bigger than me, it's way bigger than this building, then my ear isn't going to be, or this side of my head isn't going to be much of a barrier to that kind of incoming wave. Does that help? And we're going to be talking about how the size of these waves will play a role in what gets blocked what makes it to both ears and what makes it to only one of the two ears. But we'll do a little bit of that on Wednesday. Please go ahead.
Does it take longer for us to hear lower frequencies, or does the brain take like a slice of the cycle of a sound wave and then extrapolate the frequency based off of like a short example?
Yeah, that's a really good question. There is some extrapolation that goes on. And to pick up on that point, there's a really fun phenomena called the missing fundamental. As you're hearing my voice right now, my voice has a range of frequencies in it, right? If you hear my voice over a cell phone, that bottom frequency actually isn't there. And the reason for that is your cell phone has a tiny speaker that can produce really, really low frequencies. And yet you would immediately recognize my voice on a cell phone as still my voice. And so what happens is the brain actually does make an extrapolation and does have this capacity to fill in some missing information. Yeah, very good. Okay, I wonder if somebody can begin to walk us through, even crudely, this very busy slide. This is one that throws off some students. So we'll move on to phase, but if you've got this, you've got a pretty good start on what phase is. Becca's brave enough to get us started anyway. Thank you.
So starting at A,
Okay.
if that's where the waves, well, that is where the wave starts.
Okay.
That is a neutral angle of compression
Okay.
or rarefaction.
Okay,
So
so-
that neutral.
Right, in fact, just to help everybody orient on this graph, which is what we're trying to explain, way up here is compressed air. So Yuen and Jenny's hands are tightly together, and then when they're further apart, they're way down here. And Becca's correctly saying that we're not way up, we're not way down, we're in the center, so we're neutral. Okay? Great, okay. Anything else you want to add? So that's a really good start. Can you take us to B?
Yeah.
Okay, thanks.
So the I have sine corresponds to the height on the y-axis.
Yeah, who remembers that? Cosine x, sine y kind of thingy, right? Okay, all right, good. So now we've gone from here over to here. So we're at a higher point on this. 12 o'clock would be really high, 6 o'clock would be really low. So we're higher than 3 o'clock, at least vertically. Okay, so we've moved up to here, okay, right? And then we can work our way around, and then we're at 12 o'clock. If I can go to several of them down here, we're already at G, and we're working our way in this sinusoidal pattern. So this correspondence between a circle and a sinusoid. Who's seeing that? Is that working for us? So we're moving through regions of, or times of compressed air and decompressed air, and we can express that moment in time in terms of phase angle, right? And we can use either degrees. We're moving through 360 degrees in our circle. Half the way around would be 180 degrees. That would be over this far. And then also some people might be familiar with radians. Others don't like radians as much. Who remembers radians or has had exposure to radians before? Okay. All right. So we can talk about how far apart two stimuli are in amplitude or in frequency or in phase. Right? We can express that phase in some kind of angular unit shown here. And what we're really talking about is that particular sound at this moment in a compressed state or a relatively rarefied or decompressed state. And we can get to that description very, very precisely by using these angles. Okay? Okay, we have just a moment. Can anybody help us out with this really counterintuitive notion of noise cancellation headphones and how that might work? Does anybody have a explanation for that? We can go with Elise. Thank you.
So noise cancellation headphones will have the exact opposite phase of the sound you're hearing.
Okay.
So that they balance out whatever sound. So if there's background noise, the noise cancellation headphones will find so say that's compression, they'll find the rarefaction.
Yeah. Right, that's right. So if this is sort of the primary frequency that's coming in, and they might be able to find more than one frequency, but if they can find that frequency, then they can just say, all right, I'm now going to try to tag the phase. Are we in a compressed moment, a decompressed moment? And they work opposite that. They work the other side of the street very informally. And if we do a point-by-point adding, this thing always zeroes out to, or begins to zero out, and then we have no sound, or at least a reduced sound. We can reduce much of the sound here. Please go ahead, Gil.
So if you have noise canceling headphones on and then you introduce a sound that's very out of phase with the general ambient noise, it'll be able to slip through the noise.
I would think so, yeah. So this is a matter of engineering, right? So might you have multi-channels that are capable of picking up transients, acoustic transients, and then maybe you can flag those. But you would imagine there's going to be some limit to these things. Right? So they're not going to work perfectly, but in relatively acoustically stable environments they would work. Okay? All right, that was a great conversation. Thank you all for watching the videos and chiming in. I hope you're as blown away by the magnitude of your auditory system as I am. When we come back on Wednesday, we'll be talking a little bit about how the physiology now maps onto all of this physics. And again, just as a reminder, for those of you in the Tuesday class, I will be there, available for questions. Some of you might need to be running participants tomorrow. Some of you might not have participants. So you don't have to show up if you don't have anything to do in that interval. Thanks, everybody. See you Wednesday here or Tuesday.